Okay, so Chapter 6 expands on what we learned in Chapter 1. Chapter 1 provided us with a tool called Lewis structures to predict the molecular geometry and the structure of covalent compounds, okay? But there are some serious shortcomings when it comes to Lewis structures, and it doesn't explain everything. Like, for example, here we have oxygen, and when you draw oxygen, and oxygen is always diatomic, you have this, and I'll draw it so you can see it a little bit better, right? When you're done drawing it, you have a double bond, and you have two lone pairs. And so, as is the case with every Lewis structure that you draw, unless it's a radical, you are always going to have all the electrons paired up. So you can't really tell whether something is paramagnetic or diamagnetic at that point. Now, we know from experiments that liquid oxygen, which is in this door here being poured through a magnet, is actually diamagnetic. Okay, so there are some unpaired electrons, but by this structure here, you cannot explain why it would be the case. That's one serious flaw, and another one is the bond angles don't really work out, right? So here they have actually a valence bond, not a valence bond. This is a molecular orbital diagram, so that's one of the theories we'll be looking at, and then we're going to look at valence bond theory, which is tied to Lewis structures, right? So let's take a look at this molecule here, right? So we have H2S, and we're going to look at shape now, right? And so if you draw the orbital diagram, and you'll see that ignoring the lower lying orbitals, only looking at the valence electrons. Sulfur has 3s2, 3p4, right? So we know that we have a total of 6 valence electrons. And then it bonds to 2 hydrogens, as we know. And when we draw it like this. I'm drawing water now, but it's the same structure. It's just sulfur, and water could also be an example here, but this is dihydrogen sulfide. We know it makes 2 bonds to hydrogen. We also know that the angle here is a little less than 109.5, because these 2 lone pairs are going to push down. So we know that this is experimentally, and from just looking at Lewis structures, that's what it is. But if you look at an orbital diagram, you just simply cannot explain that. It breaks down, right? Because in order to make a bond, as you know already, you can pair up, you can take one of these electrons from hydrogens and put it in and pair it up with a p orbital, right? And the simplest thing that we've done is we've looked at hydrogen, 2 hydrogens overlapping to make dihydrogen. That's the simplest model that we've looked at. And so this works here as well, right? So this electron can share from an s orbital, can share with the p orbital here of sulfur. But when you do that, we also know that the s orbital is spherical, and it has both electrons in it. And then we have the px and the py and the pz orbital, which is what is shown here, right? So we have an x, y, z coordinate system. This is where this is where the p orbitals are, right? And they happen to be at a 90-degree angle. So, but we know that's just not true. And so we need to do something better than draw a Lewis structure and look at these orbital diagrams the way they are, right? So one thing I want to mention now, because I'm going to have the tendency to call this a sigma bond, okay? So a sigma bond, and I have a slide for that. A sigma bond simply means that you have a single orbital with a single electron, such as the 1s orbital here, and you overlap that with a single orbital from another atom with a single electron in it. Like, let's say this is the px, and this is the py, and this is the pz. Okay? It can do that with the py, have a direct overlap, and that's called a sigma bond. And then later on, when we make double bonds, those are going to be pi bonds. Okay, but I'm going to look into that in more detail. I just want to throw that out because I have the tendency to call those sigma bonds. And so what I mean is it's a direct overlap of 2 orbitals forms a sigma bond. Okay, so let's see how we can remedy this issue. Here again, this is even worse. Not only for methane can we not support what the Lewis structure provides us and the reality. We know that methane looks like this. We know methane has 4 sigma bonds and makes 109, makes a tetrahedron here, right? So we know that this is a tetrahedral. If you look at the electronic configuration of carbon, the central atom, we have 2s2 and then 2p. So that means we have we have 2 electrons that are paired up, and we can only make 2 sigma bonds with 2 other hydrogens, right? Because we just don't have, we need 1 electron from each orbital, right? So according to this model, we can only construct something like that with a 90-degree angle, right? And where you have 2 of the p orbitals that are simply empty, right? So that doesn't work. So it breaks down again. So what we come up with to remedy that is in valence bond theory. We come up with the concept of hybridization. We'll look at that here in a second, right? So first of all, valence bond theory just explains bonding and bond angles, and all it is what I explained already. An orbital on one atom overlaps an orbital of another atom, and that leads to lowering of the energy and stability, and so that's energetically favorable, and so we are always dealing with 2 electrons total for the 2 orbitals. And so that is a single atom. So we usually look at the central atom, so if we have, like we had methane, we look at carbon. You can look at hydrogen too, but hydrogen is just, okay, it's 1s and 1,2 and makes a sigma bond and we're done. But it's the carbon that we need to explain a little bit better. So these are then the so-called sigma bond. We have a direct overlap of one orbital with another, right? So as shown here, we have 2 s orbitals that have direct overlap, single electron here from each, making a sigma bond. You can do that with the p orbital, right? So you have a single electron here, 1s1, 3p1, just one of those p orbitals for direct overlap, and so you get this direct overlap here. There's your sigma bond, there's your sigma bond, and you can do that with a d orbital. We can do it with an s and an s, 2 p's, and so that contributes to bonding, right? And we already looked at this little model here. So we have, this is for hydrogen, H2. As these 2 s orbitals, these 2 hydrogen atoms with a single electron each, approach each other, when they start to overlap, you see a drop in energy, and then at its radius, Bohr radius, you see a drop, a stabilization. So it's going to go for this minimum here, right? So the distance between the 2 nuclei for dihydrogen here, that's the ideal. That contributes to sigma bonding to an overlap, right? So that's the interaction that's favored. And so how do we explain then the moment you've all been waiting for? How do we explain that? So if we look at the ground state for carbon, right? We have 1s2, and I'm going to cut that off because this is the complete ground state, the orbital diagram. We don't need to worry about the s electrons. They are buried and they're not interactive. And then we have 2s2 and 2p2, and Hund's rule says spread them out. That's fine. Again, the limitation is that we can only make 2 sigma bonds. So what they say is you take these atomic orbitals here and you combine them to make a hybrid orbital. The 2s and the 2p are already very close in energy, and so they blend together to make what is called an sp3 orbital. And so you take all these 4 where they all are energetically equal. It's a new orbital. They call it a hybrid orbital, and it's simple. Its designation just means it took the s orbital and all 3 p orbitals to make this happen. Now you can make 4 sigma bonds, which is exactly what we have for methane here, right? We know when we draw the Lewis structure. So that valence bond theory supports Lewis structure. Explains it with orbital diagrams here. So here your 4 sigma bonds. So when all of those hydrogens come in, once you put that in, once you put also the hydrogen atoms, and everything is always going to be paired up once you're done bonding, right? And so we don't worry about the ones in the ground states. That's essentially what valence bond theory does. It just says it takes atomic orbitals and puts them together in a hybrid orbital, right? And so that sp3 hybridized orbital looks like this here. This is in green, shows the sp3 hybridized orbital for methane, right? This is the Lewis structure over here. And then the hydrogen atoms are not hybridized. They just simply use their single electrons from their s orbitals to overlap. And so this also explains why we can have 109.5 degrees here, right? We have this hybrid orbital, and that we can do for all of the different shapes that we have, from linear to octahedral. And I'll show you how that works in just a second. Here's a really nice picture of the 3 orbitals of carbon that engage in this hybridization here, right? So you've got the 1s and the px, pz, and the py, right? And so you combine them all to form this. At the end it looks like this, as the other picture here on the left. This is the same here shown. The green here is the purple, and so they nicely pick this apart here, where they show each component, each angle, right? So here, this contraption here, that's what a tetrahedral looks like, right? A tetrahedron is just a geometric form, and so you've got in each of the corners, you've got the overlap here, or the electron density. Each of these corners has electron density, and then other orbitals, whether they're p orbitals or other. If a carbon-carbon bond is formed, you can have another sp3 hybridized model come in. But valence bond theory focuses on the central atom, like I showed here, right? So you focus on a single atom here, the central atom, and that's all. Okay, and that in itself is a little bit of a drawback, but it does help explain all the shapes. Okay, so if I can only remember what I was going to do here. Oh, okay, never mind. All right, I thought this was coming next. Never mind. Okay, so here we just have a summary of the different shapes and what kind of hybridization we need, and it's actually pretty straightforward. So what we have is we have an s orbital. We have one s orbital. For anything, right? Magnesium has s orbitals, has also p orbitals. Whether they're empty or not, they're available, right? And then we have 3 p orbitals. Let's say for the third period, let's say phosphorus has 1 s orbital and 3 p orbitals. So that can accommodate up to 4 regions. Okay? So when you make a linear shape like CO2, you have an sp hybridization, because in order to make something linear, you just have to blend 2 orbitals, right? An s orbital and a p orbital to make an sp hybrid orbital. So now that also means that you have 2 p orbitals that are unhybridized, okay? And so we'll come back to that in the middle, so in a minute. For now, all you need to look at regions, and it doesn't matter that you have double bonds or triple bonds or single bonds here, right? So there are 2 regions on the central atom and 2 regions which is linear. So this is an AB. If you remember that, AB2 systems are all sp hybridized. When you go to trigonal, you need a 3rd orbital, so you grab another s orbital. So then you have an sp2 hybridization. When you go to 4 regions, such as methane, you grab another orbital. So sp3, meaning we have 4 total for 4 regions to make a tetrahedral bond. When we go to 5 regions, we are out of p orbitals. We are done. So we need to, as I briefly threw out in the last chapter, we are going to borrow the d orbitals, right? And that also explains why we can have an expanded octet for some atoms but not others, because you have to have available, energetically low-lying available d orbitals for that expanded octet, right? Because there it is, right? So now if you have 5 regions, one of those is going to have to come from a d orbital. So that hybrid orbital is going to be an sp3d trigonal bipyramidal, right? You've got this. That means we have 1, 2, 3, 4, 5 regions here, sp3d. And so one of those has to come from a d orbital. Simple enough. You go to 6, we can take another d. In fact, we have 5 d orbitals, right? So we have 5 d orbitals. So we can actually go crazy if we wanted to and use them all. Okay, so let's take a look. All right, so these are the steps on how to draw a valence bond model for a central atom, right? I'm going to go through this step by step. I'm not going to read it. I'm going through these steps for a couple of examples, but it's there for you to look at and go back to on the slides if you need to. All right, so here we go. This is we just looked at that, right? We don't need to look at this. I'm only going to ask you to provide that and know that for the valence electrons. Just a summary here, right? So you write the ground state on the left, and that's just the orbital diagram. 1s2, 2p2, spread out the 2 electrons. Then, so the first thing you do is, of course, you want to draw the Lewis structure, because that tells you everything. Once you draw the proper Lewis structure, right, count the valence electrons, spread them all out, go for the octet, see if you need to make a double bond, done. You know that this is tetrahedral. And you know by looking at that there are 4 single bonds. These single bonds all have to be single electrons in a hybrid orbital, right? So you know you need 1, 2, 3, 4 single energetically equivalent orbitals. So that's exactly what's drawn here. And then that works out perfectly. You take the 4 electrons, you spread them out, and that works out great. Okay, now let's look at XEF4. So number 1, xenon has 8 valence electrons. Remember, fluorine 7, 4 times 7. And then you add it all up, and you find that xenon is the central atom. We draw 4 single bonds, so those are sigma bonds to fluorine, right? And when we are done spreading out the electrons, we have 4 left over, right? And I'm not gonna baby step you through this. You practice this, hopefully you watch the other lectures and you know what I'm doing now. This should be just easy and understandable, right? So I need 2 more electrons, all right? And xenon has a valence of 8, and so this is how everything has a formal charge of 0 here, and that's important too to remember that. But based on that, we know without even looking at the ground state, right? Although you will need this too, right? So you're gonna need the ground state of the central atom, and so xenon is, let's see here, 1, 2, 3, 4, 5. Oh, that's the 5th. All right, so we're gonna have 5s and then 5p. Okay, so we know this, but we also know that we here have how many regions on xenon? We have 4 bonds and 2 lone pairs, so we have 6 regions, right? So we're going to need to borrow the empty p orbitals here, right? So the 5d, so the 5d is also needed. 1, 2, 3, 4, 5, and there are no electrons in there. See, there's no way that we can predict that xenon would actually do anything. Okay, and those are rare, but they do exist. Chemists did not make these up, and so they made these xenon compounds, and they were wondering how in the world does that happen. So then they investigated and they came up with the valence bond theory, and it holds up very nicely here, right? So we have 6 regions. That means we have an sp3d2, right? 3 plus 1 is 4 plus 2 is 6 regions. So 1, 2, 3, 4, 5, 6. Technically, we also need to put the remaining unhybridized d orbitals. This is a good habit here, right? Because I'm only using 2 and there are 3 more. So I'll leave a little space and I put 1. Oh no. Let me try that again. So I have 1, 2, 3, 4, 5, 6. And then I'm going to put them down here. 1, 2, 3. These are unhybridized. Then I'm going to take these 8 electrons and I'm going to spread them out. So I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, look how sweet that works out, right? We have 4 sigma bonds. That's what these are. And we have 2 lone pairs. That's what these are. Okay? So whenever you see, and you can backtrack that, right? Without doing this and counting, you can say, okay, we have 2 lone pairs. They're going to have to be in a hybridized orbital paired up. And we have 4 sigma bonds. I need 1, 2, 3, 4. So I know I'm going to have, you can backtrack and come up with that. And then go backwards. Okay, so this is the example of XEF4, right? Let's go see what I have. Oh, this is just clean, showing you, drawn out what I just drew with all the wonderful glitches. Here's a generic picture of what that looks like here, right? So this is for the third period, right? So this is anything that's octahedral, that's silicon, phosphorus, sulfur, or chlorine, right? Because we have the 3s and the 3p, and it is the 3d orbitals that are empty, but they are low enough in energy to be populated. So that's what this is here. So it takes all of these, blends them together, puts them on an equal level, all 6 orbitals to form this octahedral shape here, right? So this is generic. It could also be square pyramidal or square planar, right? Depending on whether there are electrons here or two electron pairs to form lone pairs or single electrons. Okay, so fair enough. This is the end, and I'll come back later.